All right, let's take the prime factors problem, right? And we want to do the same thing, printing and returning a list, right? Let me just remind you of the algorithm here. Right, so we know that in the prime factors we actually minimize the n. So if I told you that there is n that is equal to, for example, 12, right, so we are actually minimizing the n. In the factors we keep the n as it is, we do not change the value of n at all, right? So in the prime factors we said that we start with 12 and try to divide it with something like, for example, I, the smallest prime number, right, which is in this case the smallest prime number is 2, right? So you divide 12 by 2, right? So this is going to get you what? This is going to get you 6, right? So this means that 12 is divisible by I. So this means that this I is a factor. So I equals 2 is a prime factor, not only a factor, right? And that result is what we are going to use as my new n. So notice how n is going to be changed, right? So n is divided by that I. Alright, so it's just as saying that n is divided by I, and I will tell you in a minute why did we use the interdivision, right? It's gonna serve with this algorithm, right? So we have 6 right there, right? So try to divide 6 with the same I, right? This is gonna get you what? This is gonna get you 3. And this means that 6 is divisible by 2, so this means that this 2 is another prime factor that we can either print or append into a list, right? Now this is going to get you 3, right? So let's take that 3, right? And let's say that I'm going to divide 3 by 2, right? So now this is not going to work. This is going to get you something like 1.5, right? So there is a remainder, and this is an indication that it is not divisible. So 2 is not divisible. In a case like this, you tend to increment the I with 1 and try to divide the same n again, right? So if you incremented the I with 1, so I is now 3. So try to divide it now. This is going to get you what? This is going to get you 1, right? No, remember, we are doing interdivision here, right? So all right, so this is going to have 1, right, which means that this 3 is a prime because 3 is divisible by 3. So this I, when it's equal to 3, is a prime factor, right? Now let's divide 3 by 3 using the interdivision as we said. This is going to get you 1, right? Now try to divide 1 by 3. Well, typically this is not going to work because now the number, which is n, is less than that I. So my base case can be obviously something like this. If I got bigger than n, we can stop, right? Or if n got equal to 1, then we can as well stop, right? I'm not going to go through all the details in this program because we did this in the lab in very much detail on Canvas, and I think in the next week of the semester, or the second week of the semester. So I'm just going through this just for you to remember what did we do with or how did we approach this algorithm, right? So let's just write this iteratively. Iterative prime factors, right? And let's say that we wanted to use a while here because we didn't really know when to stop. We didn't really know when will that n reach 1, right? Or we didn't really know what kind of i's that we will have here, right? Like here we have like some 1, 2, 3, 4, 5 iterations. This is 5 iterations. You cannot tell using a for loop. A for loop is used when you have a limited number of iterations that is already known for you before you start the algorithm. But if your algorithm is being derived via dividing the actual n or multiplying the actual n, which puts this algorithm in the category of O of log of n, right? So this means that you do not know the number of iterations. You do not know when will the 12 be 6 or when will the 6 be 3. You do not know the number of iterations when n is being divided every time by I. Since this division does not actually happen every iteration, this division happens specifically when we have something that is divisible, If we find I that is divisible, then divide and drive the next iteration, right? So when the number of iterations is unknown for you, it is better to use a while loop, right? So let's say that this is my while loop, and I'm going to continue as long as n is greater than or equal to 1. All right, so let's say that n here is 12. Okay, I think this is not totally correct. We need to keep on going as long as n is greater than 1. All right, so let's have I starting at the least or the smallest prime number, right? So let's say that if n is divisible by I, then this means that, yeah, let me just mention that we are doing the printing version, right? So we're gonna print I, and we need to drive the continuation of the iteration, meaning that if it's divisible, then now minimize n, right? By dividing n by 2, or I'm sorry, in this case dividing n by I, whichever this I would be, right? But else, if we divided n by I like 3 or over 2 and it's not divisible, then in this case we need to keep n as it is, but let's just increment I by what? By 1, right? So this is going to give you 2, 2, and 3, right? And if you looked at the recursive version, you're going to see that the whole idea is being repeated over and over again. So let's say that this is primes function, and primes takes n, and it should typically take as well I, which is the first prime factor, which is 2 in this case, an optional parameter, right? So we would use the same structure here, right? So let's just define the base case. The base case for me is that when I find that, as I told you here, n is less than I or n equals to 1, when I find that I kept on minimizing n way too much until n is 1, this is an indication for me to return what? This is an indication for me if I am printing to return nothing. Notice that we are printing in this version. This is an indication for me to terminate the program, right? Because in this version we are only looking for printing, primes print. And just take this copy like that, right? And let's say if n is divisible, I'm just going to repeat the same body right there, right? So if n is divisible by I, right? So in this case, just call, first of all, just print the I, and now drive the minimization of n to go to the next iteration or to go to the next recursive call. So we have primes print being called once more, and we are passing to it n divided by 2, which is what's happening there, right? Or I'm sorry, divided by I, and we are passing the same I. There is no need to change the parameter I in this case, right? But else, what if it's not divisible by 0? And this means that I'm just gonna call the primes print, but in this case n is not gonna be changed, right? N is gonna be passed again, but what's going to be changed is actually I, right? So let's try and call primes print and give it 12. It's gonna give you the same exact result, right? There is no need for you to do the first method and the call stack in this case, because it is literally the same, right? And what if I wanted to do the printing or the returning version? Let's do the returning version on the iterative first. So this is the return a list version. Return a list version, right? So instead of that, right? And instead of this, we could have just said that we have L that is empty list, and instead of printing, we can just append into that list. I'm sorry, append I into that list, right? And when we print that list, you should see the same result. Let's take the recursion version, and let's call it primes, only primes, that returns a list, right? And it should take a positional argument that is an empty list, like this, right? And we changed the name to primes, and this is a list, right? And this is a list a list as well, and instead of printing, we're just gonna take a list and append to it I, like that, and we're gonna say that we have an empty list and pass it to primes. All right, now let's print whatever this is gonna return, and notice something, this is gonna return none, right? This is gonna return none because now you want to return something. It's the same exact thing that we discussed over the facts program. So if you didn't watch the facts program, please watch it and come back to the primes factors next, right? And try to trace this on a pen and paper, just like the way I did with the facts in the previous video, right? So in this case, I actually care about returning a list. So here, I just want to return the list. I don't care about just terminating the program. Well, yes, I want the base case to terminate the program and as well to return that list that I've been appending into from the start of the program, right? So this is gonna have a permanent return here, and this is gonna have a permanent return here. One of these returns is gonna be executed. That's why I'm calling these permanent. I know that this is conditional and this is conditional, but one of them by the end of the day is going to be executed. Where in every iteration, where this is going to only happen only once, because this is the base case. So if we run this, you're going to see that the returned list is going to be 2, 2, and 3. If you didn't understand this, again, please go back to the facts version or the facts return a list version, where I did this in the previous video, and you're going to understand why did we have a return before the recursive call inside the function. And just the way we did with the factors, we do not really want to depend on the user for sending the empty list, and we can just initialize it once like that as an optional parameter, and it would still work.